Hello, class. I'm starting chapter 3. Let me see. Okay, so I go back ebook. I repeat the step. I'll let you see the chapter summary. Chapter 3 summary. We have done chapter 2 summary already. So chapter 3 summary, and then we will watch the lecture together. Okay. So summary. For chapter 3, you will learn about let me see. Chapter 3, we learn about radiant measure. Okay, radiant measure. And then the section 3.1, you will learn about reference angle. Okay, so for reference angle, notation in this textbook is theta, and then they have the hat. Or any angle theta. So theta represent for the angle in the standard position. So, and remember, positive angle would be counterclockwise, and negative angle would be clockwise. So remember that. So the example will be on the left side. As you notice, we have too many. We have four. We have four angle right here. So to figure out the reference angle, so let's look at the definitions. The reference angle theta hat for any angle theta in a standard position is a positive. Remember, positive. Okay, so all the time will be counterclockwise. A positive acute angle. So acute angle is mean the angle have to be less than 90 degree between the terminal side of theta and the x-axis. The terminal side will be the angle that stop, right? And the x-axis, we're talking about this line, the black line. Okay, so to find the reference angle of something or theta hat, for the example that we are having is the following. So they given us 30 degree is the reference angle for all four of this angle degree, 30 degree, 150 degree, 210 degree, and 330 degree. So this is just one example. They showing us 30 degree is the theta hat or reference angle of this four degree angle. So let's look at the example here. We have, for example, if I'm giving you 150 degree and I want you to find a reference angle. So what you're gonna do is, so let's do one example for you, and you watch more video from the lecture, okay? Okay, so I'm having, let me see right here. So let me draw the x-axis, all right? And you have the y-axis right here. So if we want to find the reference angle of 150, so now the standard position theta angle is 150. So we have theta is 150 degree, right? So where is it? So here start from 0 degree right here. So counterclockwise, so we go that direction. So this is 90 degree, and this is 180 degree, right? So 150 will be smaller than 180. So around here. So let me use different color. I'm pretending it's right there. Okay, right here. Right, so the 150 will be from here to here. So which is right here. So that is 150 degree. Or in other words, you can write this as theta, right? So we have the standard angle, angle theta in the standard position is 150. To find the reference angle of this, I'm gonna use different color, maybe this brown color. So based on the definition, have to be a positive acute angle, right? And have to be the terminal size between the terminal side and the x-axis. So here is our terminal side. This is our terminal side. And this is the x-axis. terminal side right here and the x-axis. So this here, the red angle right here, we call the theta hat. I wrote the arrow telling you that I go that direction, which is the positive, right? Positive angle. So this will become, what you can do is you take, so the whole round will be 180, you minus 150, you got 30 degree for this theta hat. So theta hat, which is the reference angle, it will be 180 degree minus 150 degree, you got 30 degrees. Okay, so that becomes the reference angle. So that is one of the example. So and so on. You want to get into detail, then you can go back the textbook at the beginning and you can see the process. Okay, so here I'm showing you one example so that you can practice the other three, and later we'll watch the video together. Then you will see more. Okay, let me move down. Let's see. So we have the second the concept is reference angle theorem. So we have the theorem. So this theorem is given us. It's like you using the reference angle with the standard position angle, because reference angle help you to compute quickly the angle of theta, side of theta. Okay, so for example, right here, some problem want us, they give us very huge number. For example, like they give us sine 150 degree. They want us to figure out this value, and in order to figure it out, so you can find a reference angle of 150, which is 30. So you can figure out sine 30 is what value. So sine 30 degree based on the special table, so it will give us 1/2. Okay, so those values we should memorize. So sine 30 degree is 1/2. So you can check this on table in chapter 2, right? Uh, and uh, and remember as well as the quadrant. Okay, remember the quadrant? Me. The quadrant, we have quadrant 1, quadrant 2, right? Quadrant 3, quadrant 4. So we have the negative value for sine or cosine. Then you need to check the degree. For example, we're talking about 150 right here is in quadrant 2. Quadrant 2, if we're talking about sine, right? If we're talking about sine value, the sine value stand for the y-axis, correct? So this means is will be the positive value for sine 150 will be equal to 1/2. Okay, by using reference angle is sine 30 degree, we have the value is 1/2. Another example, for example, sine of 210. 210, as you notice, is down here in quadrant 3, right? So we're doing the same process, the same steps, and you notice that side of 210, again, the reference angle is still 30 degree. So we're gonna have the y-axis right down here is negative value, so you got a negative value for side 210, and the final solution will be negative 1/2. So for doing this exercise, you cared about the quadrant as well as the reference angle. Okay, and let's move on. And I would like to erase this so that we have space. All of this again will be repeated with the video that we will watch together, so no worry. But if you want, but I suggest that you copy it down as detailed as you could, and highlight it so that you can remember which and which. Radiant measure. So for radiant measure, we're talking about like for radian, like relate to like pi divided by something, or so you need to know how to convert that. So right here, starting with the radian measure. So in the circle, as you notice, we using the circle now to doing the art. We're talking about the art, about the angle of the center. So O right here will be the center. Okay, so in a circle, a central angle that cuts off an arc equal in length to the radius of the circle has a measure of 1 radian. So this is like a standard, um, like all the time. That is the definition all the time. When we are having the central angle that cut an arc with they have this angle right here. Let me see the angle right here. Okay, have the equal length. Uh, so this angle will be equal with the arc right here. So that's what geometry. That's what you should know. That's why I say right here that are equal in length. Okay, to the radius. Right. The radius is right here. That's equal to the radius. So r here, if r is 1, so the r here is 1 too. If we have the um, like they cut off like that. So all the time the length will be the length of for the radius from the center to the circle, whatever value here, uh, should be equal to here too, because we have the small circle and the big circle depend on they given us the value. But in this case right here, if we're talking about a unit circle, we have radius is 1, then this should be 1. And usually they apply unit circle to figure out the side and the angle apply for trig to figure out trig. To the radius of the circle has measure of 1 radian. So 1 radian right here, they have a value. Later you will see the conversion, like how do they convert 1 radian to degree and stuff like that. So right here, the notation, the angle theta is right here has a measure. Theta right here has measure of 1 radian. So which is look like is equal to r right here is equal to 1, but even though they don't write 1 exactly because the circle changing. Okay, they might give us a theta is different angle, and then that value of the length right here will be changing depending on the circle. So the vertex of theta is at the center of the circle, and the arc cut off by theta is equal to the length of the radius. So that is how they demonstrate. Okay, the example is down here, radian and degree. So this is what I'm talking about. The radian they convert to degree, degree convert to radian by using the formula. So changing from degrees to radian and radians to degree is simply a matter of the multiplying by appropriate conversion factor. So as you notice right here, from degree you want from degree, they multiplied by pi divided by 180 degree. So this all the time represent for number one. Okay, so pi divided by 180 degree. So this is number one. So in order to convert, so that's why it's helping us to convert easily. Or they can switch up if you want to convert from radian to degree, then you multiply by 180 degree divided by pi. So they like you switch over. So an example is that on the left side, if they given us, they want us to change radian 4 pi divided by 3 into degree. So what we need to do, radian into degree, you multiply by 180 degree divided by pi, right? So you can cancel pi, and you got 180 divided by 3 down here, you got 60 above, right? 60 and then times 4 right here, you got 240 degree to convert into the degree. And the opposite. In order to, they're giving us from the degree to the radian, you need to multiply by pi divided by 180 degree, then you can cancel out. So I recommend you should write this example down and formula so that you can easily remember it. And the unit circle. The unit circle all the time is helpful. So for the unit circle, you see now R become is 1 now, right? So the unit circle, the point on the circle, they want us to notate at x comma y, or represent for cosine theta comma sine theta. So this helping us to um, compute quickly the angle, the size. This is another way. This is another way for help us to find trig. Okay, so the unit circle is a circle with its center at the origin, right? And the radius is 1. That's a unit circle. The equation of the unit circle is all the time is x squared plus y squared equal to 1. Or cosine squared plus sine squared equal to 1. So because of the radius of the unit circle is 1, any point x comma y on the circle will be like this. X will be equal to cosine theta and y will be sine theta. I'm sorry, that go back. All right, so we are having the even and odd function. Even and odd function. If you learn in, I think it's okay. Never mind. I don't know algebra class they have talked about this. But for the even function, if you got a negative input all the time when you plug in the system, they all the time give you the function fx. Okay, and the odd function, which is if you plug in a negative input, you will have a negative function of f of x. That's give you, for example, cosine of negative input all the time give us the even function, a positive. And sine will give us a negative sine theta. So sine theta will be odd function. And in order to prove this, actually, if um, the shape of cosine is showing us the even function, and the shape of sine will be showing us odd function to the left unit, like the or the negative unit is kind of showing us there will be a negative sign, negative value of arc length. Arc length is appear when you have the circle. So let me give you an example. All the time you got a central, right? Central, all like this. So arc lengths appear when we make theta or something. You got this small arc length, okay? And we have a big arc length. So arc length is S. So let's just say S1 and S2, which is different color. Let me draw a different color for you. See that? So the total will be 360. So the formula, if let me see, the formula for the arc length is the following: S equal to R stands for radius, and theta stands for the angle. Okay, so if S is an arc cut off by a central angle theta, measured in radians, in a circle of radius R, then you're having this. So this formula you should write somewhere. And the example is on the left side as well. And in the lecture, you will see more application about this, okay? Area of the sector. So the area of the sector, which is, if we're talking about area, it means like we're talking about the shaded part, right? So for example, I'm having this angle. So we wanna find the area of a sector. You wanna find this. We're using this formula, okay, to figure it out. Okay, so the example right here, we say the area of the sector formed by a central angle, right, of 2.5 radian, which is, for example, I've just named it 2.5 radian right there. Central angle is O. In a circle, radius is 4. I'm sorry, the angle of 2.5. I'm sorry, this is not the radius. The radius is 4. The radian is 2.5. Okay. And we have the following. So we got A equal to R squared, theta, which is the angle right here, which is 2.5. You multiply all of it, you got the shaded area like this. We call the area of the sector. Linear velocity. Linear velocity. Linear velocity. Let's see. So they talking about a formula. So right here, it's look like different story right now. So V stand for velocity, and we're talking about linear is mean is the example is might be we talking about like the clock relate to the clock, for example, is one of the example about linear velocity. We have the minutes, minutes hand and hours hand and second hands. So that's kind of, we're talking about linear. So, and another example right here, they're talking about a point moving at a uniform speed on a circle travels 12 centimeters every 3 seconds. Then the linear velocity of the point will be apply this formula. They will give us S. S stand for the uh, um, art, right? Art, and then divided by S stand for the I think the speed. Let me see. If P is a part of the circle radius R, so R is a radius already. P move a distance S. Okay, so for this case, S now is not second or not the value that I mentioned. S here in linear velocity will be represent for distance, right? Represent for distance. So V stand for velocity. Velocity will be distance divided by the time. T stand for the time. Stand for the time. V stand for linear velocity. So this formula is really um, common. So I want you to copy this down. So from here you can imply. You can imply is what? If you want to find S, right? If you want to find S, so let me pretending. So if you want to find S, so the formula will be V times T, okay? But if you want to find T, what, for example, then you will have S divided by V. So you can copy that this three formula in so that is you can easier quicker to compute to find V then to find V apply formula distance divided by time, and to find S you will have the velocity times time, and if you want to find for the time you would take the distance divided by V. Okay, so there's three formula for you. You can copy down somewhere on your notes and try to write the topic as well, because every topic, every concept, sometimes they give us different meaning of the letters, the symbol letter. So I want you to write the topic for me and copy that formula so it's easier for us to follow. The angular velocity. Angular velocity is kind of related to linear velocity, but angular and linear velocity kind of related. The differences is, let me see. The differences is they give us different formula now. Omega here stands for angular velocity. Theta is the measure angle in radians, and R stands for radius. And we have two formula right here. So right here, the angular velocity, let me see, let me read one more time. If P is a point moving with a uniform circular motion on the circle of the radius R, and the light from the center of the circle through P sweeps out the central angle theta in the amount of time t, and the angular velocity omega. Okay, so that's right. So omega here represent for angular velocity of P is given by the equation below. And the relationship between a linear velocity and angular velocity is the follow. So V is equal to R times omega. So that is, they said the relationship between linear and angular is that. And the example is on the left side, please. If you're curious, spend time reading over it. Actually, for this type of problem, you just like apply the formula, identify which one and which, and then from plug in the formula. So okay, so let's go ahead now and watch the video together. 3.1, reference angle.
If angle theta is in standard position, then the reference angle for angle theta is the smallest angle between the terminal side of theta and the positive and the x-axis. Let's take a look. Here we have 120 degrees. We want to draw it in standard position and then name the reference angle. So if I go around my coordinate system, if my angle in standard position terminated here, that would be 0 degrees. If it terminated straight up here, that would be 90 degrees. Over here, 180 degrees. And down here, 270 degrees. If I went all the way around and made it back to here, that would be 360 degrees. So the angle I'm talking about is 120 degrees. That's between 90 and 180. So I'm going to draw it in right here. Here is 120 degrees. That's my angle theta. The reference angle for angle theta is the smallest angle between the terminal side of theta and the x-axis. I think I said the positive x-axis before. That's not quite right. It's the x-axis, period. So here, to go from 120 to 180, that's going to be 180 minus 120, which is 60 degrees. So the reference angle for angle theta, I'm going to say is theta with a little hat on it, is 60 degrees. So when 120 degrees is in standard position, then its reference angle is 60 degrees, and that represents the smallest angle between the terminal side of theta and the x-axis. Here's our next problem. Find the exact value of cosine 225 degrees. So again, I'm going to go around my coordinate system here. This is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back to here would be 360 degrees. So 225 degrees is between 180 and 270. So I'm going to draw it in right here. Here's my angle, 225 degrees. And then its reference angle is right here, 45 degrees. That's 225 degrees minus 180 degrees is 45 degrees. So the cosine of 225 degrees is going to be equal to, now, I know that my angle terminates here in quadrant 3. In quadrant 3, my cosine function is negative. So I'm going to put a negative sign in here, and that's because of quadrant 3. And then I know that the numerical value for cosine 225 will be the same as the numerical value for the cosine of its reference angle, 45 degrees. So I have the cosine of 225 is equal to the opposite of the cosine of 45. Cosine of 45 I've memorized. It's 1 over square root 2. So drawing this little diagram right here kind of helps us visualize where our angle terminates. Then we find the reference angle. The numerical value of the trigonometric function of an angle and its reference angle will differ at most in sign. So here I know cosine 225 will be the opposite of the cosine of 45. I've memorized cosine 45, that's 1 over square root 2, so my answer is just negative 1 over square root 2.
For number 2, you can find the reference angle by taking 270 minus 225. You got a 45, right? So you can figure out the reference angle like that.
My next problem. Find theta if sine theta is negative 0.3090 and theta terminates in quadrant number 3. So I'm going to work on a calculator here. I'm going to say, okay, sine theta is equal to negative 0.3073090. Now I'm going to enter just this on my calculator, press my inverse sine button, and I'll end up with my reference angle. So if I just put the numerical part in without regard to the sign and press my inverse sine button for 0.3090, I'll end up with my reference angle, which in this case comes out to be 18 degrees. So that's what my calculator gives me. Now I know that theta terminates in quadrant 3. Its reference angle is 18 degrees. Remember, this is 0, that's 90, and they're degrees. 180 degrees, and 270 degrees. So I'm in quadrant 3 with a reference angle of 18. I'll draw this in. This is 18 degrees. So my whole angle theta right here must be 180 degrees plus 18 degrees, which will be 198 degrees. So angle theta comes out to be 190 degrees, and I found it by knowing that sine theta is negative 0.309, and theta terminates in quadrant 3. If you just input negative 0.3090 on your calculator, press your inverse sine button, you won't get the correct answer. You'll end up with negative 18 degrees for the answer because of the restrictions on my inverse sine button in the calculator. So we have to do it this way. Here's one more problem.
And remember for number 3, we're talking about reference angle all the time. You have to thinking about the angle that closer to the x-axis, okay, or positive angle counterclockwise with between the terminal size and the x-axis. So that's why you got 18 close to the x-axis.
Find theta if sine theta is negative square root 3 over 2, and theta terminates in quadrant 3. So again, here's 0 degrees, 90 degrees, 180 degrees, 270 degrees. Sine theta is equal to negative square root 3 over 2. My square root 3 over 2, along with the sine function, tells me that my reference angle is going to be 60 degrees, because the sine of 60 degrees has an exact value of square root 3 over 2. So here's my reference angle. I want to be in quadrant 3 with a reference angle of 60. So I'll draw that in. This tells me that theta itself must be 180 degrees plus 60 degrees, and that will come out to be 240 degrees. So same kind of problem as problem number 3, except I'm using exact values here, and I know that I've memorized the fact that the sine of 60 degrees is square root 3 over 2. So I forget the algebraic sign to begin with and just let this numerical value here give me my reference angle. Then from that in my little diagram, I can find the actual angle itself.
So that all the negative for 3.1. If you have any question, again, please let me know in class or email me. And let me keep moving on. 3.2. 3.2 is about radians and degrees.
If angle theta is in standard position, then the...
Oh, I think we did this. We just did this, right? So now is 3.3. Let me see. So circular function.
Here's our third definition for the trigonometric functions, and it involves the unit circle. Now I've drawn the unit circle over here on a coordinate system. The equation of the unit circle is x squared plus y squared is equal to 1. It has a radius of 1. That's why the coordinates of this point are x equals 1, y equals 0. Now if I start at 1, 0, and I move t units along the circumference of the unit circle and end at any point whatsoever x, y, then here are the definitions for the trigonometric functions. The sine of t, that is the sine of this arc length here, t, is equal to y. So that y coordinate is the sine of this arc length t. The cosine of t is equal to x, and the tangent of t is y divided by x. So you can see tangent of t is still sine t over cosine t. Now, and the definitions for cosecant, secant, and cotangent are such that I can get these reciprocal identities out that I've had before. So cosecant is 1 over y, secant is 1 over x, cotangent is x over y. So these are new definitions for the trigonometric functions. It's our third definition, and it involves the unit circle. Now, t is not an angle here. It's real number measure. It's a length along the circumference of the unit circle, starting at 1, 0, and ending at the point x, y. If I'm on the unit circle, then the coordinates of any point on the unit circle are cosine t and sine t. Now, what I want to do is take a close-up shot of this and see if we can go back and draw in a diagram so we can get our original definition 1 for the 6 trigonometric functions back. So suppose I draw in this angle in standard position here, theta, angle theta. Now theta in radians is going to be the arc length t divided by the radius of the circle, which is 1. So theta and t are exactly the same thing. That is, the radian measure for angle theta and this arc length here, t, are exactly the same. So you can even think of t as being angle measure. Now let's go back to our original definition one for the trigonometric functions and find the sine of theta. Let's have a close-up here. So the sine of angle theta, well, theta is in standard position here. So all I need is a point on the terminal side. Well, xy is on the terminal side. The sine of theta is the y-coordinate divided by the radius, which is 1. That just comes out to be y. So you see that sine theta is equal to y, whether I use my definition 1 or this definition 3 that I just wrote. Now let me go back to this diagram and see if we can't draw something in and see what we can get for the sine of theta using definition 2. I'm going to draw in a vertical line right here so I get a little right triangle. So here's my right triangle. Here's angle theta. It's an acute angle in this right triangle. The length of this side is x, and the length of this side is y if this is the point xy. Now I'll use definition 2 to find the sine of theta. The sine of theta, using definition number 2, will be the side opposite, which is y, divided by the hypotenuse, which is 1, so I end up again with y. So the sine of theta is equal to y no matter whether I use definition 1, definition 2, or this new third definition. So 3 different ways to define the trigonometric functions. All of them are consistent with each other, and one works well if we have the point on the terminal side of an angle in standard position. The second definition works well if we're working with right triangles, and this third definition works well if we're on the unit circle and gives us a way to have a real number measure for angles here. I can think of finding the sine, cosine, and tangent of an actual real number length right here. So as you'll see as we progress through the course, these 3 different definitions come into play in different situations. Let's go to the board now and look at our first problem. Let's use the unit circle to find all the trigonometric functions for 11 pi over 6. Now, what I've done is reproduce this little diagram out of your book of the unit circle that has all the angles, their corresponding radian measure, and then the ordered pairs where the terminal side of those angles intersect the unit circle. So here's a nice close-up of that. Now, here's 11 pi over 6 right here. Let me just draw a line in at the terminal side of that. It's right here, 330 degrees is 11 pi over 6, and I have the ordered pair square root 3 over 2 and negative 1/2. So let me write that right here. Square root 3 over 2 and negative 1/2 is the ordered pair at 11 pi over 6 units from the point 1, 0 along the unit circle. So that's the point, square root 3 over 2, negative 1/2. Those are the coordinates of the point where 330 degrees intersects the unit circle, or you can also look at it as the coordinates of the point that are 11 pi over 6 units along the circumference of the unit circle away from the point 1, 0. In any case, this is the cosine of 330 degrees, or 11 pi over 6, and this is the sine of that angle. So writing the 6 trigonometric functions is going to be very easy. The cosine of 11 pi over 6 is square root 3 over 2, which means that the secant of 11 pi over 6 is going to be its reciprocal, 2 over square root 3. Now let's see how much room I have, okay? The sine of 11 pi over 6 will be the x-coordinate, will be the y-coordinate, negative 1/2. So the cosecant of 11 pi over 6 will be the reciprocal of that, negative 2. Then the tangent of 11 pi over 6 will be the sine divided by the cosine, and the cotangent will be the reciprocal of that. So this diagram right here, as far as finding sine, cosine, and tangent of all these angles here, whether they're written in radians or degrees, turns out to be a very simple process. You just look at the coordinates of that ordered pair. The x-coordinate is the cosine of the angle. The y-coordinate is the sine of the angle. Let's look at another problem now. Problem number 2, let's find all theta for which cosine of theta is negative square root 3 over 2. So I'm just going to use the unit circle over here to find all the values of theta for which the cosine of theta is negative square root 3 over 2. So if I look on my unit circle, cosine of theta is the first coordinate of all these ordered pairs. So I simply want to look around for ordered pairs that have a x-coordinate of negative square root 3 over 2. Okay, here's square root 3 over 2. I keep going around. Here's negative square root 3 over 2. That's 150 degrees, or 5 pi over 6 radians. Keep going. Here's another negative square root 3 over 2 at 210 degrees or 7 pi over 6. And that's all we should find because x coordinates are only going to be negative in quadrants 2 and quadrant 3. So by looking at the unit circle, I know that theta must be equal to, what was this, 5 pi over 6? Or this angle right here, which was 7 pi over 6. So a lot of these problems are just to get you familiar with using the unit circle to find cosine and sine of some of these special angles that are written in either degrees or radians. The next thing I want to do is talk about sine and cosine as being even and odd functions. Let's look at the next problem. But first, let's define what an even function is and an odd function. Remember from algebra, an even function is a function for which f of negative x is always equal to f of x. So you can replace x with negative x. It doesn't change the function values. If that's the case, you have what's called an even function. Now, cosine is an even function because the cosine of negative theta and the cosine of theta are exactly the same thing. Now, odd functions are such that f of negative x is negative f of x. So if I replace x with negative x in an odd function, my function values change signs too. So if f of negative x is negative f of x for all x for which the function is defined, then we have what's called an odd function. And now the sine function is an odd function because the sine of negative theta is always negative sine theta. For instance, the sine of negative 30 degrees is the opposite of the sine of 30 degrees. Sine of 30 degrees is 1/2. The sine of negative 30 degrees, that will be in quadrant 4, that's negative 1/2. So sine of negative 30 is negative sine 30, and that's why the sine function is an odd function. Now, next what I want to do is work a couple of problems that involve this definition, or I should say these functions. But anyways, let's try problem 3. Let's find the cosine of negative 5 pi over 6. Well, cosine of negative 5 pi over 6, because cosine is an even function, is the same as the cosine of 5 pi over 6. And now if I check on my unit circle, which I don't have right here, but if I just look on my unit circle, the cosine of 5 pi over 6 turns out to be negative square root 3 over 2. Negative square root 3 over 2. So here I use the fact that cosine is an even function to write cosine of negative 5 pi over 6 as just cosine 5 pi over 6. And I do that because cosine is an even function. Then I use the unit circle or whatever other means I have to find the cosine of 5 pi over 6. That turns out to be negative square root 3. Here's our third definition.
Let me explain a bit about the last part, number 3. If we are imagine cosine of negative 5 pi over 6, you know that is the negative angle, right? So if but you know cosine is even function, so it will become cosine of 5 pi over 6, and 5 pi over 6, you can figure out that value by finding the reference angle, which is cosine pi over 6, right? So cosine pi over 6 is square root 3 over 2, but then why is negative? Why is negative? Because of is in the second quadrant, right? 5 pi over 6 will lie in the second quadrant, less than 180 degree. So that's why you are having a negative value for cosine. Okay.
Because cosine is an even function, then I use the unit circle or whatever other means I have to find the cosine of 5 pi over 6. That turns out to be negative square root 3.
All right, class, for the proving tangent is odd, you don't have to worry about that. So this is, I think, let me double check one more time. I think this, 3.3. So we do have 3.4 and 3.5, and we're done. Okay. 3.4, we learn about arc length and area of the sector. And by using the formula, it's very simple. So let's watch
Here
this.
is a circle with a radius of r and a central angle theta that cuts off an arc of length s. Now, area A stands for the area of this sector right here. Here's the formulas I have if theta is written in radians. The radian measure for theta, as you know, is the arc length s divided by the radius r. That means that the arc length s is going to be r times theta as long as theta is written in radians. So if I multiply both sides of this by r, I get r times theta is equal to s. So here's a formula that allows us to find arc length if we're given the radius and the central angle measure in radians. The area of that sector is 1/2 r squared times theta, and again, theta has to be measured in radians. So we want to work with these formulas right here. The new one is really an old formula written a new way for arc length, and then area of a sector, that's a new formula. Let's go to the board and work our first problem. Suppose that theta equals 60 degrees as a central angle in a circle with a radius of 4 millimeters. Let's find the arc length S cut off by angle theta. So let me draw a little picture over here. This will be my circle. I have a central angle that will be 60 degrees. The radius of this circle is 4, so that's 4 and that's 4. And what I want to find is this arc length S. Well, I know my formula for arc length tells me that S is equal to R times theta, as long as theta is written in radians. So let's put in R, that's 4 millimeters, times theta, which is 60 degrees. And then I'll just convert 60 degrees into radians by multiplying by pi over 180 degrees. So what I end up with here, let's see, I'll divide 60 into 180, that goes 3 times, 4 pi over 3, and the units will be millimeters, and then I can convert that into a decimal using my calculator, and that will come out 4.19 millimeters, or that's approximately, I should say, 4.19 millimeters to the nearest 100.
So for S, which is arc length, all the time the units should be radian. So which is numbers or pi involving. So for this case, pi in this case is 3.14. You can take 4 times 3.14 and divide it by 3. You will get the value the same. Okay.
So 4.19 millimeters or 4 pi over 3 millimeters. In either case, that's the length of this arc S that's cut off by a central angle of 60 degrees in a circle that has a radius of 4. Here's our next problem. Theta is equal to pi over 4 this time, so it's given in radians. S is equal to pi centimeters. Let's find R. So remember, theta is a central angle in a circle that has a radius of R, and then theta cuts off an arc of length pi. So let's draw a little picture right here. Theta will be equal to pi over 4, so I'll just draw this angle in here, and this is pi over 4. And I have, I'm looking for R, that's the radius of the circle, and I'm given S is pi centimeters right there. Well, let's use our formula for arc length. Arc length is S is equal to R times theta. So I have S, it's pi. I'm looking for R, and I have theta, which is pi over 4. So I'll multiply both sides of this equation by 4 over pi. So let's do that. 4 over pi, 4 over pi. When I multiply, the pi's divide out over here, and I end up with R is equal to 4, because these all divide on this side. So R is equal to 4, and let's see, what are the units on this? Centimeters. So if I have a circle in which a central angle of pi over 4 radians, which would be 45 degrees, cuts off an arc of length pi right here, then the radius of that circle has to be 4 centimeters. So if I cut off a arc of pi centimeters, then the radius is going to end up to be 4 centimeters if that central angle is pi over 4 radians. Let's look at a problem now that has to do with a clock. Suppose the minute hand on the clock is 2.4 centimeters. Okay, how far does the tip travel in 20 minutes? So let's suppose here that I have the minute hand of a clock. Suppose it starts right there and then travels and then goes for 20 minutes. So from here to here, it takes 20 minutes. Let me see if I can get this right here. And suppose that this is 2.4 centimeters. Well, we can think of this as being a central angle in a circle of radius 2.4. And so what I want to know is the distance that the tip of the minute hand travels. So I want to know, what is this arc length right here? Arc length S. Well, I need to find this angle theta, so let's see. Theta is equal to, well, this is 20 minutes. Once around would be 60 minutes, so 20/60th times 2 pi. I know once around the circle will be 2 pi radians for this angle right here, and so I'm going 20/60th of that, so I'll have 20/60th times 2 pi. That will be my angle theta, and theta will be in radians. So S, the distance it travels, is R times theta. R is equal to 2.4 times 20 over 60 times 2 pi. And let's see, I can divide out these 10s here, so I get 2, 6 times 2 is 4. I'm going to have to write down here, so 2.4 times 2 times 2 is 4, 6, so 2 pi over 3. This is multiplication right here. I better write it like this. Let's see, I'm going to try to divide this 3 into 2.4. 3 into 2.4 is going to go 0.8 times. Let's see, so 0.8 times 2. Okay, how about 1.6 pi as the exact value of the distance it's traveled? And what have I got here? Centimeters. So 1.6 pi centimeters, or if I want to multiply 1.6 times pi, let's see what I have here. That comes out to be 5.03 centimeters. So I should say approximately equal to 5.03 centimeters. So if you have a clock and the minute hand of the clock is 2.4 centimeters long, then in 20 minutes, the tip of that minute hand must travel about 5.03 centimeters. And it looks about like that's what it should be. If that's 2.4, that looks like it's going to be a little more than twice that long in 20 minutes. Let's look at our next problem. Here we have theta is 15 degrees, r is equal to 5 meters. Let's find the area of the sector formed by theta and the circle. So to draw a little picture over here, here's my circle. Theta is equal to 15 degrees, so that's this angle right here, 15 degrees. And r is equal to 5, so that's 5 and that's 5. What I want to find is the area of this sector, the area of this little piece of pie right here that I have. So my formula for that is A is equal to 1/2 r squared times theta. So A is equal to 1/2 r squared times theta, and theta must be in radians. I have 15 degrees for theta. I'll convert to radians as I go. So I have 1/2 times 5 squared times 15 degrees times pi over 180 to convert from degrees into radians. So this is what the setup looks like. Now let's see, I have 25 times 15 times pi over 2 times 180. Let's just see what this is. 25 times 15 times pi over 2 times 180. 15 will divide into 180 12 times. So let's say I have 25 pi divided by 2 times 12 is 24. So 25 pi over 24. And my units were meters, so this is going to be square meters, and that will come from right here where I have 5 meters. Quantity squared is 25 meters squared. So I'll put in the units there. That is the exact value.
So class, over here, like I explained earlier, the area all the time, I think the area all the time have to be like something square, right? It have to be radian. So the reason is because here is we have degree, right? So we have degrees, so we have to find somehow that convert this data into radian. By how? By multiplied by pi divided by 180. So pi divided by 180 actually is number 1, okay, 1 radian. So that's why you can convert from degree. So he missing the degree right here, e and the degree for 180. So we have to convert by multiply by that so that we can have the value in radian. Otherwise, you all the time get the degree. That's wrong. So, and remember, over here, if they're giving us like 15 only, then you don't have to multiply pi divided by 180, okay? So because the 15 already a radian, but from this case, 15 degree is not radian. So you have to multiply by pi divided by 180 to get the answer. And the unit have to be meter squared because our unit is in meter.
Value of the area of that sector, and let's see if I want to write this as a decimal, it comes out 3.27 meters squared. Now does that seem to make sense? This is 3.14 times about 1, so yeah, 3.27 square meters. So if I have a central angle in a circle, it measures 15 degrees, the radius is 5, then the area of that sector that it cuts off by this formula, 1/2 r squared theta, is approximately 3.27 square.
All right, class, I think we have one more last section. Let's see. Let me double check, okay? Did we odd length and area? Yes. The last section will be velocity. velocity, I already gave you 3 formula for it. So
in this section, we're going to talk about uniform
let's
circular
watch.
motion. And you have to imagine a particle moving around the circumference of a circle at a uniform rate. That is moving at a constant rate around this circle. Now, theta is a central angle in the circle. The radius is r, and this arc length is s. That would be the amount of distance the point would travel on the circle in a time t. Now, the linear velocity, if the point goes from here to here and covers this distance s in a time t, then the linear velocity of that particle is v equal s divided by t, just distance divided by time, and that will be our linear velocity. The angular velocity is the amount of angle rotation that this goes through in an amount of time t, and that's defined as omega, which is, by definition, theta, the amount of angle that you go through in time t. So it's this angle theta right here, measured in radians, divided by t. The relationship between linear velocity and angular velocity is the linear velocity is the radius times the angular velocity. If you want to see the derivation of this, you have to look in the book. So imagine that this point P travels a distance of, let's say, 5 feet in 2 seconds. Then its linear velocity is going to be 5 feet divided by 2 seconds, or 5/2 feet per second. If the amount of angle that it goes through, let's say it goes through pi radians in 3 seconds, then the angular velocity is going to be pi over 3 radians per second. So let's go to the board now and work some problems that involve uniform circular motion. Suppose that the distance s that's traveled along the circumference of the circle is 12 centimeters, and it takes 4 seconds to do that. Let's find v. Well, v is equal to s divided by t. That's going to be 12 centimeters divided by 4 seconds, and that will come out to be 3 centimeters per second. Now, what that looks like is, suppose we have a circle, and a point travels from here, let's say, to here, and that's a distance of 12 centimeters, and the total amount of time that it takes to do that is 4 seconds. Well, then, the linear velocity of that point along the circle is going to be 3 centimeters per second, because it goes 12 centimeters in 4 seconds, so its linear velocity is 3 centimeters per second. So linear velocity is pretty easy to find. It doesn't depend on the radius of the circle. All we need is the distance traveled and the amount of time t. We divide distance by time, and we end up with linear velocity. Here's our next problem. Suppose, on the other hand, that the velocity is 20 feet per second and the time t is 4 seconds. You want to find the distance that's traveled along the circumference of a circle using this uniform circular motion. Well, I'm going to use the same formula. V is equal to s divided by t, and I'll simply substitute in v is equal to 20, s is what we're looking for, and t is equal to 4. So I substitute those numbers in, I multiply both sides by 4, and I end up with s is equal to 80 feet. Now let's see if that makes sense real quickly. Suppose I have a circle. Okay, I have a point that's moving along the circumference of the circle at a uniform rate, and it covers 20 feet every second. How far is it going to go in 4 seconds? The distance that it's going to travel in 4 seconds will be 4 times 20, or 80 feet. So I can still use the same formula right here, and it does make sense intuitively when I think about traveling around a circle at a constant rate of 20 feet every second. If I travel for 4 seconds, I'm going to cover 80 feet on the circle. Now, we don't know how big or small the circle is, but we do know that we're covering 20 feet around the circumference of the circle every second. So I just substitute into the formula anyways, and I get s is equal to 80 feet.
Or you can write s at v times t. You got the answer is 80 feet. 80 feet. Okay.
Let's look at another problem. Suppose that the angular velocity, omega, is 4 radians per second. The radius of the circle is 2 inches, and the amount of time that the particle has traveled is 5 seconds. Let's find the distance that it's traveled. Well, I'm going to start with my formula for v, and v is equal to s divided by t. Now let's see, I'm looking for s, and I'm given t, so I've got part of this filled in, but I need v. Well, v is also equal to, besides s over t, the other formula is r times omega. So s over t must be equal to r times omega, because v is equal to s over t, and v is equal to r times omega. So let's substitute in using this equation right here and see what we get. So s divided by t, so I have s divided by 5. is equal to R, which is 2, times omega, which is 4 radians per second. So I get S is equal to 2 times 4 times 5. When I multiply both sides of this by 5, 2 times 4 is 8, times 5 is 40. And that's 40. Let's see, S is my arc length. I have radians per second and inches, so this is going to be 40 inches. So if I have uniform circular motion in which a point is traveling around the circumference of a circle with angular velocity 4 radians every second, the radius of the circle is 2 inches, and I let this thing go for 5 seconds, the total distance that I'm going to cover is 40 inches around the circumference of the circle. Let's look at our next problem. 10 RPMs is what omega? So by this I mean 10 revolutions per minute. What I have here is RPM stands for revolutions per minute is what as an angular velocity? Because a lot of problems in real life you see are given in terms of RPMs or revolutions per minute. So let's see how we can convert RPMs into angular velocity and then use that. We could solve a lot of other problems. Here we go. So I have 10, and I'm going to write this as revolutions per minute. Now I'm going to multiply this by a conversion factor that's going to have me end up with radians per minute. So what I have is this. 2 pi radians are in 1 revolution. So 1 complete revolution around the circle is 2 pi radians. You can see that my revolutions will divide out right here, and I'll have 10 times 2 pi, which is 20 pi radians per minute. So 20 pi radians per minute is the same as 10 revolutions per minute, and that will always be the case. So I can change from RPMs to angular velocity anytime I want by multiplying by 2 pi radians per revolution. The revolutions will divide out here, and I'll be left with radians per minute, which is the units for angular velocity. So that's a quick look at linear velocity, angular velocity, when we have uniform circular motion and the relationship between those two velocities.
Okay, class, thank you very much. We have finished chapter 3. And again, if you have any question, please let me know. Email me, or you can, ask your friend around. We read a textbook. Yes, and that's it. So chapter 2 and 3 have 1, 2, and 3 have completed lecturing. So waiting for chapter 4, 5, 6, 7 to come. Okay, see you next time.